Welcome friends to the 17th lecture on module 2 on the NPTEL course on risk and reliability. Of offshore structures. We are talking on lectures in module 2 which is focusing on reliability theory and structural reliability. Today we will discuss lecture 17 in module 2, where we will continue with the application problem what we discussed in the last lecture. So, application 2 I will say continue. So, we are talking about the effect or the influence of the response of a compliant system under highly nonlinear waves in the presence of earthquakes. So, the original PM spectrum, which is a function of wind velocity, is modified. So, the original Pearson-Moskowitz spectrum, which is a function of wind velocity, is modified as a function of modal frequency. Okay. Subsequently, it is further modified to accommodate as a function of significant wave height and the modal frequency. Okay. This was suggested by Mitchell 1999, which we discussed also in the last lecture. I will write down the equation for continuity S eta eta omega 8.1 10 power minus 3 by omega 5 exponential minus 1.25 omega m by omega the power 4. Equation number 1. In this case, g is g square here. So, in this case g is acceleration due to gravity, which is 9.1 meter per second square. Omega m is called the modal frequency. In this study, in general, as advised by Mitchell, we have taken modal frequency as 0.46 radians per second, which amounts to 0.07 hertz. Okay. S eta eta is the power spectral density function of the wave height and the wave frequency. The wave elevation eta t is realized as a discrete sum of many sinusoidal functions. While doing so, we vary the angular frequencies and random phase angles. So, eta t is given by which we have seen in the last lecture as well. This is going to be a summation, discrete sum of various sinusoidal functions. Okay. So, we know that k I is the wave number, omega I is the discrete sampling frequencies, delta omega I is omega I minus omega I minus 1, which will give me the difference. N is the number of data points, and phi I is the random phase angles. Okay. Now, interestingly, the generated wave profile is designed to have a peak at a specific time t naught, which is going to be distinctly high in comparison to other wave heights, and therefore, can be classified as distinctly high C waves. Okay. If we look at the figure which is shown on the screen, one can see here the top one shows the generated Pearson muscular spectrum using the modified values given by Mitchell. The corresponding wave height in terms of wave height time history is shown here. If you take a blow up of any specific wave height or sea surface elevation, which you see from here, you can explain the characteristics of this very easily by looking at this figure, which is classified as distinctly high sea waves, because one can see here the wave height at a specific value is phenomenally and comparably very high with respect to the preceding and succeeding wave heights. Okay. So, one can simply say this is a typical distinctly high sea waves. Okay. So, the figure showed the Pearson muscular spectrum and the sea surface elevation sample at let us see x is equal to 0. So, the location is at x is equal to 0, where the wave first interferes with the structure. Okay. In this case, it is going to be a TLP. One can see a magnified wave history, sea surface elevation, see on the screen here a magnified wave history, one can see here. By looking at this, the wave generated can be easily seen as a continuous function of time near the chosen time interval. Okay. The time interval chosen in this case is t is equal to 4 seconds to t is equal to 14 seconds. In this time interval, in this specific time interval, one can easily see it has become a continuous function of time. It is also seen that the generated wave has a concave front. Okay. The generated wave and a convex rear, which is a very classical identification of distinctly high sea waves, which can cause impact on the structure as given by Kim et al. 1997. One can also see the spatially varying high sea wave profile is the wave seen in the first mode point of TLP, that is x is equal to 0. Therefore, from that point onwards, different phases of the same wave profile reaches at different positions along the TLP as the wave passes away. Okay. That is how the discrete sum of sinusoidal functions has become a continuous function in terms of a wave, which is causing a required impact on the structure, which is distinctly high sea waves. Now, in the study, the example problem or the example structure taken considered is a tension like platform kindly look at the figure shown in the screen now. This is an example TLP which is considered for the study presently. The TLP has got 3 column members designated as 1, 2 and 3 and 3 pontoon members designated as 3, 4 and 5 and 6 which are located at the bottom, and of course, the top is having a truss system where the top deck is assembled to that of the column members as you see in the elevation. The water depth is marked as D. The TLP in triangle has the dimensions in plan PB and PL, okay, plan along the breadth and plan along the length, and that is the mean sea level or still water level what you see. CG is taken at the mass center where the degrees of freedom are marked. So, one can see here the initial pretension is about T naught and the water is about dz as marked here. Now, in the equation of motion, of TLP under distinctly high sea waves is given by mx double dot plus cx dot plus kx is going to be f of x x dot x double dot, because I am going to include the acceleration as well, and of course, the time of t. Okay. M is the mass matrix of the given system, C is the damping matrix, K is the stiffness matrix, and of course, F is the hydrodynamic force vector. The structural mass is assumed to be lumped at specific degrees of freedom points, and therefore, it is going to be diagonal in nature, because we all know when the structural mass is lumped at the points where degrees of freedom are marked or measured, then the mass matrix will be diagonal. So, the mass matrix in this specific case is going to be like this. These are essentially the lumped mass at respective degrees of freedom, where M11, M22 and M33 is the total mass of the platform, whereas M44, M55 and M66 are actually the total mass moment of inertia. About x, y and z axis respectively. On the other hand, M44 is going to be simply M r x square, whereas M11, 22 and M33 can be simply said as M. Similarly, M55 will be M r y square and M66 will be M r z square respectively, which can be. Interestingly, the added mass term will also get now included in the mass matrix. So, we say plus M A11, that is going to be the added mass, which I am doing it here, and M A phi 1 the added mass. Similarly, because of the heave the displaced volume MA 33 and MA phi 3. Remaining all terms which has not been indicated here will be marked as 0. So, one can see here the additional mass matrix terms essentially arise because of the variable submergence effect on the given problem. Okay. Rxx or Rx, Ry and Rz are radii of gyration about the respective axis x, y and z respectively. Ma11 and Ma33 are the added mass terms in the surge and heave degrees of freedom, whereas Ma phi 1 and Ma phi 3 are the added mass moment of inertia due to the additional mass in surge and heave degrees of freedom respectively. The heave added mass on the TLP hull is taken equivalent to the mass of the hemispherical volume of water. Okay. So, the added mass in heave degree of freedom is actually taken equal to the mass of hemispherical volume of water. One can say equivalent to mass of hemispherical volume of water as suggested by Chakrabarty and Hanna. One can see here from the mass matrix that the presence of off diagonal terms indicates contribution of added mass due to aerodynamic loading. Okay. So, now we are talking about an example problem where the TLP is encountering the wave with front two columns in plane. So, triangular configuration in plan. Of course, it has got the top deck supported by the members and the bottom pontoon, which all now position restrained using teethers. Of course, the top deck has the same facilities as that of a conventional hull, where all systems will be present as expected in a given system of TLP. Okay. Now, interestingly, in this particular equation or the study, contribution of added mass is taken up to the MSL, which is included along the force vector. Okay. The stiffness matrix now, which is indicated as K, depends on tether tension and is response dependent as well, depends on tether tension and structural response. Okay. So, for a triangular TLP, the stiffness matrix 6 6 and k 4 4 remaining all members are 0, k 5 1, k 5 5 remaining all members are 0. In this case all members are 0 except 6 6. So, one can see here that heap degree is coupled with almost all degrees of freedom, because 311 to 36 all are present. So, heave has got a very strong coupling with almost all degrees of freedom. It is very simple to understand that concept. In case if you have a TLP, when you give an horizontal motion to TLP, the TLP actually sets and offsets and sways. When it surges or sway, of course, because of the heave movement there is going to be an offset. So, heave, surge and sway are anyway coupled. Because the variable submergence effect, there will be going to be an additional mass moment of inertia cost, and that is going to cause a restoring moment in the pitch, roll and yaw degrees of freedom. Therefore, heave is coupled almost with all degrees of freedom here. So, it has got a very strong coupling with all degrees of freedom in a given system. One can also see, looking at the coefficients of the stiffness matrix, one can easily see they are going to be teacher tension dependent and response dependent. One can see these details from my papers published and indicated in the NPTEL website. So, coefficients of stiffness matrix can be derived from the first principles. Kij can be derived from the first principles. One can easily see it from the literature. Chandrasekharan and Jain 2002. Damping matrix see in this case is assumed to be proportional to initial values of mass matrix and stiffness matrix. So, C matrix is given by a Rayleigh model combination of this, which is A01 m plus A1 k. I call this equation number 2, where A0 and A1 are essentially the stiffness, the mass and stiffness proportional damping coefficients. The damping matrix given here is interestingly orthogonal, because it permits modes to be uncoupled. By the eigenvector associated with the undamped eigenvalue problems. Okay. The damping constants A0 and A1 interestingly are chosen as fractions of critical damping. At frequencies which are omega 1 and omega 2. Okay. So, one can solve the simultaneous equation which I am going to write now. A0 and A1 can be written like this twice zeta 2 omega 2 minus zeta 1 omega 1 by omega 2 square minus omega 1 square, whereas A1 is twice of omega 1 omega 2 zeta 2 omega 2 minus zeta 1 omega 1 by omega 2 square minus omega. So, I call C equation number 3. So, the damping coefficients zeta 1 and zeta 2 are taken as certain percentage of critical damping. Okay. The corresponding frequencies omega 1 and omega 2 are chosen in such a manner. So, the two different frequencies are chosen out of 6. So, that a suitable mass and stiffness proportional damping can be used in the Chauffin system. So, the damping attributed to A0k increases the increasing frequency, whereas the damping attributed to A0k increases with increasing the frequency, whereas A1m will decrease with increase in frequency. Okay. So, accordingly one has got to calculate the values of A0 and A1, so that when you substitute here as A0m and A1k, they are compromised. Okay. So, this was of course referred from Chopra 2003. So, by taking damping as critical of 0.05, that is 5% of critical damping, the coefficients A0 and A1 are worked out, okay, are computed by solving these two simultaneous equations, okay, for surge and yaw degrees of freedom. That is omega 1 is related to surge and omega 2 is related to yaw degree of freedom. Then subsequently a free vibration analysis performed okay, to find out the natural frequency of the platform, which can be used here for our calculation. Therefore, the damping ratios can be obtained. It has been seen that the damping ratios maintain a reasonable value with all other modes. So, one has got to also check the damping ratios maintain reasonable values with all other modes. The force vector f of t is given as f1, f6 transpose equation number 4, where f will be the force in any respective degree of freedom. The first degree of freedom is of course surge and 6th degree of freedom is of course the yaw motion. Okay. The dynamic buoyant force is given by which is also going to be the function of time. It is for the equivalent TLP. So, 3 by 4 rho x of t, equation number 5. Wave forces are modeled using modified Morrison equation, which is given by so f of t is force per unit length. By d square by 4 rho Cm u double dot plus or minus pi d square by 4 rho Cm minus 1 of x double dot. Equation number 6, where x indicates the structural displacement, velocity and acceleration of the structure, u indicates that of the water particle kinematics. So, one can see here in equation 6 u dot minus x dot, in equation 6 u dot minus x dot is the relative velocity component, is the instantaneous relative velocity component between the structure and the water particle. Okay. Of course, x dot and x double dot are the structural velocities and acceleration respectively. D is the diameter of the member of the cylinder, rho is the density of seawater, CdCm are the drag and inertia coefficients which are used in the equation. The water particle kinematics u dot and v dot using the modified PM spectrum. Okay. The force vectors updated at every time instant for its response dependence and also to account for variable submergence. As you can see here from this equation, it also depends on the response, which of course not known. We have got to solve this using iterative scheme or numerical procedure. So, therefore, solution to equation of motion becomes iterative, and nu max beta time integration method is used in the present study. Okay. Now, interestingly, the force vector has got two components comprised of one. The hydrodynamic forces arising from distinctly high sea waves as obtained from the modified PM spectrum which I showed you earlier. Okay. In addition to that, it is also got the varying tether tension which is caused by the vertical and horizontal seismic excitation when the T0 or the tethers are actually anchored to the seabed. When the seabed has got vertical and horizontal seismic excitation, the tension in the tether continuously varies, which affects the stiffness coefficients. Therefore, the equation of motion is updated at every time instance, because it has got two force components now. One is the hydrodynamic force arising from the distinctly high sea waves, which we obtained from the modified PM spectrum. The second is of course the T0 variation, which causes indirect force, okay, on the system. Now, the tether tension variation which affects the stiffness coefficient is very simple. The tether tension coefficient which is affecting or influencing the stiffness matrix coefficients, okay, is dynamic in nature. It varies with time, okay. it needs to be updated and it is given by, let us say that variation delta t is given by, of course, the ratio of x of t minus x g of t, the ground displacement. Okay, let us call this as equation number 7, where x of t is the instantaneous response vector of the TLP and x g of t is actually x 1 g of t 0. I am looking only at the horizontal and vertical seismic excitation. We assume that the horizontal excitation happens only in such degree, in sway it is not there. Okay. Remaining all other degrees remains 0. Okay. X 1 of g is of course the horizontal ground displacement in such degree of freedom, and of course, x 3 of g is the vertical ground displacement in heave degree of freedom respectively. Okay. So, now we are going to add both the forces that are arising from the distinctly high sea waves, the hydrodynamic force, and the indirect force caused by the change in tether tension given by equation 7 as delta t, because change in tether tension affects the stiffness coefficients, which of course is a part of the equation of motion, which we will see and discuss in the next lecture. Thank you very much.